Thank you for that. Our next three talks will be about circumplanetary disks, and Claire Finley is going to come up and give us our first one about these, a wide orbit planet that seems to be accreting as observed with Hubble and JWST. So please join us, Claire, from UT Austin.
Is it on?
Sometimes you need to hold it up.
Test. Is this on? Okay, cool. Let me move it up a little bit then. Okay. Hi, thank you for that introduction. My name is Claire Finley. I'm a third-year graduate student working with Brendan Bowler, and I'm excited to talk to you today about the synthesis of accretion and circumplanetary disk properties of a wide-orbit planet, and I'll be focusing particularly on HST imaging today. So the exact timing and mechanism of giant planet formation remains an open question in the field. Perhaps these objects formed like the smaller terrestrial planets by the core accretion mechanism, or for objects in sufficiently cool and massive protoplanetary disks, they may have formed from a gravitational instability in the disk. Or for the very widely separated and free-floating planets, they may have formed from the collapse of a molecular cloud core or filament like a failed star. But regardless of how these objects begin, the final stages of mass transfer onto the gas giant planet are facilitated by its circumplanetary disk, or CPD. Over the past several years, we've had a handful of detections of circumplanetary disks with a reported disk fraction of about 50% for the long period or widely separated planets, yet many of their basic properties remain poorly constrained. So to remedy this, we launched a program to study the diversity of accretion and circumplanetary disk properties over a range of ages and masses, along with whether there's any correlation between accretion properties and disk properties. And we aim to do this for the first time at a population level with a uniform framework. Our program consists of multi-wavelength photometry, which we will use for all the objects in our sample. We have several objects in the sample. We will construct SEDs with broad wavelength coverage for all of these objects, and we can use these SEDs to calibrate circumplanetary disk properties, which will allow for future follow-up with higher resolution using instruments like MIRI-MRS. To put some of the goals of this program into kind of a more tangible context, I'm showing a diagram here of accretion from a disk onto a pre-main sequence star, which we can use as kind of like a proxy or a basis for how this might look in the planetary mass regime. So some of the questions that we can ask with this program are, through what mechanism does gas accrete from the disk onto the central planet? Does this follow the magnetospheric accretion paradigm like what's shown for this star here? Or does it look something more like the boundary layer accretion paradigm? What is the characteristic timescale of accretion onto these objects, and is this process stochastic or dynamic at all? For example, we know in the stellar regime that accretion stochasticity correlates with the decay of the infrared excess, but this is unknown for planets. More specific to the disk, we can ask how diverse the bulk properties of CPDs are, and if they correlate at all with any of their host planet properties, such as mass. And last, we want to constrain on what timescale do CPDs dissipate and by what mechanism, and do they decay similarly to disks around stars. Today, I will present results for one case study from our larger sample, and I'll be focusing on these more accretion-related questions on the left-hand side of this diagram using HST imaging, and then after this, my collaborator Yalin will give a talk diving into the JWST MIRI photometry that we have. So over the past decade or so, we have unlocked this ability to witness the process of planet formation by directly imaging accreting protoplanets as they form, effectively giving us this window into the process of planet formation. I'm showing here 3 images, of course, the PDS-70 system we all know and love, and then the 2 new candidates, 2MASS J1612b and WSPIT-2b. All these systems shine brightly in H-alpha, which is interpreted as strong Balmer line accretion that is indicative of Balmer line emission that is indicative of an accretion disk. To characterize the accretion properties of a system, the best thing you can do is search for an excess of emission in the UV, Lyman, Balmer, and Paschen continua, like what is shown on this model spectrum on the left here that is indicative of an accretion shock. However, for most systems, this is not accessible with UV imaging due to the technical constraints with imaging too close to a host star or with insufficient contrast. So a complementary tactic we can turn to that is a little less specific to the continuum is searching for these hydrogen emission lines like H-alpha and Paschen beta. And indeed, we see for both bound systems like GQ loop B and GSC 6214b, as well as the free floater CHA 1107, this strong Paschen beta emission that is indicative of ongoing accretion. In addition to studying the accretion properties of a system, we can look at what the environment from which it is accreting might look like, the disk itself. And a great way to do that is by looking at the thermal excess that is associated with the warm dust in the CPD with instruments like JWST MIRI, and this has been very successful over the past year or so, giving us these great mid-infrared spectra of the planetary mass companions YSIS-1b and DeLorme-1abb, as well as the planetary mass companion / brown dwarf companion GQ loop B, and of course PDS-70b and C. But one caveat with this is that all of these systems host planets that are relatively close to their host star within about 1 arcsecond, which makes it kind of difficult to dig in and study the disk properties in detail for any sort of larger population for planets like this. So as an alternative venue, what we turn to for our larger program is the very widely separated companions that are hundreds to thousands of AU from their host star to kind of subvert this problem. So we begin with a test case. This is SR12C. This is a young, about 2 million year old accreting planet located 1200 AU from its host binary in the Rho Ophiuchus star-forming region. It has a mass of about 13 Jupiter masses near the deuterium burning limit and a spectral type of L0, so we can think of this kind of as a long period beta pic B analog. And its host binary has component masses of about 1.5 a solar mass, respectively. Something that's interesting about this system is the large amount of data that we have amassed on it over the past decade or so, covering this wide range of the electromagnetic spectrum. So we have optical through infrared spectra from X-Shooter that shows hydrogen emission lines that are indicative of ongoing accretion, as well as a host of near-infrared imaging and spectroscopy that confirm the low mass and youth of the system. And then we also had archival Spitzer data that hinted at a circumplanetary disk around this planet. But what's missing are the furthest reaches of this planet's SED, the UV, where we search for the accretion properties of the system, and the mid-infrared, where we want to characterize the disk. To address the former, I present here new HST with C3 imaging from about 2200 to 6600 angstroms. We recover the companion in all 5 filters that we image in, so the first 4 indicate an excess of continuum emission, and then the last filter shows H-alpha emission in the F656N filter. We also marginally resolve the host binary in all filters, and we use this to constrain interstellar extinction to the system. So with the addition of this new data set, we can kind of cover the left-hand portion of the planet's SED, and then with the addition of the MIRI data that Yellen will be describing after this, we can fully cover the electromagnetic spectrum for this planet, making it one of the broadest wavelength coverage SEDs of a giant planet to date. So this is what the photometric SED looks like, particularly with our 2 new data sets added. And before we begin to model this emission, it was important that we had an accurate estimate of the extinction to the system because this heavily impacts the UV photometry that we'll be using to describe the accretion properties of the system. So I fit models to photometry of the host binary and derived an extinction coefficient of about 0.9 or 1 magnitude. So we deread in the photometry as such, and that's shown in the colored in or filled in symbols, and the white or open symbols were the observed photometry. So to begin to model the emission from the system, we anchor a photosphere model to the J-band photometry where this young object is expected to emit its peak thermal emission. This model had an effective temperature of about 2600 Kelvin and a surface gravity of 3.5. And with this added in, it becomes really clear how both the UV and the mid-infrared are in excess of the photosphere and can't be described by the photosphere alone. To describe the accretion properties of the system, we use hydrogen slab models following Valenti in 1993, which approximates the accretion shock to the planet as an isothermal slab of hot hydrogen. We use these models instead of the more sophisticated accretion shock models because in this case we are lacking details of the geometry of the accretion column. And also we are primarily seeking to kind of anchor the continuum and integrate underneath it to obtain a bolometric accretion luminosity, owing to how coarsely sampled our photometry is and the large scale of the uncertainties. So this works for our purposes. These models have two parameters of the temperature of the hydrogen slab as well as the number density of hydrogen atoms in the slab. And they adjust the size and slope of the Balmer jump respectively. So the Balmer jump is the spectral feature at 3646 angstroms. It's a sharp decrease in flux that happens when the hydrogen gas is ionized by the accretion shock. So to test which model best describes the accretion properties of our system, we employ a custom MCMC framework, which allows us to see the kind of family of solutions that could work for this system, the best fit model of which being plotted here in like the black highlighted spot, but we can also see all the other models that the MCMC tested, which gives us a idea of the scale of the uncertainties. We can add this best fit hydrogen slab model to the SED and see that it begins to describe a little bit better the emission from the system, of course with the caveat of the large uncertainties, but certainly better than the photosphere alone. So taking the best fit hydrogen slab model in combination with the H-alpha line accretion luminosity, this gives us our total accretion luminosity for the system, which is about 2 times 10 to the negative 5 solar luminosities. This translates to a mass accretion rate of about 1 times 10 to the negative 11 solar masses per year. So to put that number in context, that means that if this planet continues to accrete at this mass accretion rate, over the next million years, it will only gain another 0.01 Jupiter masses, which tells us that SR12C must have formed all of its about 13 Jupiter masses in its short 2 million year lifetime. We can add this mass accretion rate to the small yet growing sample of planetary mass objects with mass accretion rate measurements, specifically from the UV continuum excess. All this data in the best fit line is from the Caspar database. And it has been theorized that potentially if future measurements of planetary mass accretion rates follow this trend of plateauing off to the left and being higher than the best fit line, that may be indicative that these objects formed by the disk instability paradigm and had higher initial masses. Or it may just be that we are biased to only the highest accreting objects right now given technical limitations. But what's clear is that we need to fill in this parameter space a little bit more, which is what the rest of our program will do. Last, we had 2 epochs of HST imaging taken about a month apart, so we investigate any potential variability in our measurements. We find a 26% decrease in the H-alpha flux over the month baseline, which is significant to about the 2 sigma level given the large uncertainties. Additionally, for the bulk UV continuum, we see some slight modulation there too, but again, given the large uncertainties, we can't conclusively say there's any variability in the UV. But when compared to an epoch taken 4 years earlier from X-Shooter, we see a 90% decrease in the H-alpha flux over these 4 years, which backs up the recent theoretical prediction that variability is expected to be more significant over longer baselines. So with that, we find this unique framework of jointly modeling the accretion and circumplanetary disk properties allows us to constrain not only how much a giant planet is accreting, but also what the environment it accretes from looks like. And I just wanted to remind you again that this is only one small part of a larger sample, so please stay tuned for those results. And I'll just splash up my conclusions here. Happy to take any questions.
Okay, thanks very much, Claire, for the talk, and very well delivered. So do we have questions from the audience? Okay, well, I'll make an initial question. I saw there was a long wavelength millimeter wave point for this object.
Yes.
Does that translate into a mass estimate for the disk?
Yes, this is an ALMA point, and Yalin will be talking about that, so stay tuned.
All right, questions from the audience, questions online? Oh, sorry, go ahead.
I'm wondering about what are your thoughts on, are these wide separation planetary mass objects different in terms of accretion from normal planets, or are they the same as field stars, like very low mass field stars accreting?
That's a good question. I think that's something that will benefit from more observations. I think we don't have enough of a sample, particularly for anything closer in than these planets, to be able to say, at least with the continuum excess method, whether there's any kind of functional difference between them.
Orbital inclination? How are we viewing the orbit?
There is some astrometry of the host binary, but because the planet is so long period, it wouldn't be practical to like observe that much orbital motion for it.
Other questions here or online? Okay, I guess we'll move on to your colleagues, so thank you very much.